Okay, welcome to today's INQA seminar on the 22nd of October. And I'm delighted to have Michał Wroński will be giving the presentation today on first practical quantum solution of the discrete logarithm over prime fields. Over to you, Michał.
Okay, thanks for invitation. Thanks for introduction. So as I told Paul, I'm working in two institutions. The first one is Scientific and Academic Computer Network National Research Institute. The second one is Military University of Technology in Warsaw. So these both institutions are in Poland. And as you see, I will be talking about transformation of the discrete logarithm problem to the QUBO problem. So I won't be talking about quantum annealing because I think that most of you know very well what quantum annealing is. I will be using quantum or simulating annealing, it no matters, as a black box. So I want to efficiently transform some cryptographic problem, in this case, discrete logarithm problem, to the QUBO problem. As you know, then QUBO problem may be solved, for example, using quantum annealing. So okay. So in here's outline of my presentation. I will tell a few words about QUBO problem. Then I will show some example how to solve linear congruences. So it will be good introduction to the next section, which is about discrete logarithm problem over prime fields and how to transform this problem to the QUBO. And then I will make some summary and I will tell what maybe further works. So I think that this seminar won't be too long. Paul asked me to talk no more than 30 minutes. I think that it will be not a problem in this case. So QUBO, as you know, is quadratic unconstrained binary optimization problem, and it may be expressed by the matrix, quadratic matrix Q of the dimension time n times n. It is upper temporal matrix with real coefficients, and x is a vector of binary variables. So in this case, in here we have the diagonals, coefficients, and these are diagonals are linear coefficients, and non-diagonal terms are such coefficients. And of course, QUBO may be presented as a function minimization problem in such a way. So I think there is no required more introduction here. So maybe I will show some example. So I'm interested in how to solve the following linear congruence. It's worth to note that linear congruence is the kind of discrete logarithm problem. The main part will be about computing discrete logarithm problem in the multiplicative subgroup of some finite field, prime finite field FP. But the congruence, like here, is a discrete logarithm problem in the additive group of some, in this case, prime field. In this case, it is field F23. So let's think about how we can transform this problem efficiently to the QUBO problem. At first, let's note that that x must be some element from the set from 0 to 22. I will show it for a minute. So maybe equation first may be transformed to the equation over integers. So if we have in here 7x is congruent to 3 modulo 23, we can write it equivalently as 7 times x plus 20 minus 23k, and it has to be equal to 0, of course. So because x is element from 1 to 22, because 0 cannot be here, 7 times 0 is congruent to 0. So we can write x using 5 bits in such a way. You can see that in this case x may be also equal to 0, but it's not important, because only for the proper result the final QUBO problem will return the global minimum. Yes, so the global minimum will be equivalent to finding the proper solution. So we can write x using 5 binary variables. Yes, because in QUBO problem, of course, we have binary variables 0, 1. So it is the first step. So the equation from the previous slide may be written as is presented in here. So 7 times this is x, 7 times x plus 20 is equal to 23k, or as I wrote here, minus 23k is equal to 8 is equivalent. So what next? We have to find what is the maximal value of k, because in here k is some integer. Yes, it is integer. We cannot have in here integer because it's variable. We don't know what is the value of k. So we also have to write k using binary notation. So we make following computation. We will estimate the maximum value of k. So at first, if all variables from u0 to u4 are equal to 1, we can estimate what is the maximal value on the left side. So it is 7 times 22, yes, because if all these variables are equal to 1, we have 22 in here. So the left side at most will be equal to 7 times 22 plus 20. It gives 174. So we can use this, we can find the maximum value of k. It will be floor from the 174 divided by 23, and it is 7. So k is some integer from the set from 0 to 7. And we know that such a number may be written using 3 bits or equivalently 3 binary variables. So k is equal to u5 plus 2u6 plus 4u7. So finally, our equation takes the following form. Oh, it is something like this. Of course, it is equal to 0. And if we want to solve it using quantum annealing, of course, we cannot solve directly this equation. We have to square this equation. Yes, I hope maybe I will show why. So let's try to find look at very simple example. X equals to 5. Yes, of course we can try. We may transform it to x minus 5 equals to 0. But if we will write this function, let's suppose that x belongs to real numbers, then we obtain something like that. Yes, so we cannot find a global minimum because the minimum is minus infinity. But if we will square this equation, then we of course will find something like that. So we will obtain quadratic function, and therefore if we will find the global minimum of this function, we will therefore find a solution of this simple equation. Yes, So in here, it is identically. So we have to, at the end, square it, and we'll obtain some quadratic function. We can then run it using quantum annealing, and we will find the solution. So do you have any questions now?
I have a quick question. I didn't follow where this 20 came from. Can you just go back a couple slides?
Okay, yes, okay.
I missed the 20.
Okay, I will. So we
Yeah,
have
here.
7 times 6 is congruent to 3 modulo 23. Sorry, I didn't tell. So we move this 3 to the left side. So minus 3 modulo 23 is 20.
Perfect. I get it.
Okay?
Thank you.
So that's why it's 20. I'm sorry, I forgot to
No problem.
about that.
Thanks.
So I hope that it's clear how we make this transformation. So this is a simple example. Yes, simple example, simple linear congruence. So of course, yes, I told we square this equation, we obtain BQM with a minimum energy of 0. Of course, if we have BQM, we can easily translate to the QUBO. Only the monomial of degree 0 should be the and then we can use every method: simulated annealing, quantum annealing, probabilistic annealing, whatever you want. So now I will tell a few words about discrete logarithm problem. So we can define discrete logarithm problem like is presented here. So g to the power of y equals to h. But let's look that we operate in some prime field fp. So p is prime. G and h belongs to the multiplicative subgroup of this finite field. And I wrote in here that y is some integer, but in real, y will be limited by the order of element g. So we can translate this problem equivalently to the following. So g to y is congruent to h modulo p. So I think that you see that is something similar to the previous example, but in here there is a little problem because we have y in exponent. Yes, y is unknown, y is in the exponent, so I will show for a moment how we can deal with it. Of course, integers g and h, because they belong to the multiplicative subgroup of this field, they are from the set from 1 to the p minus 1. Okay, so why this problem is important? Many cryptographic algorithms are based on the discrete logarithm problem. The most popular is Diffie-Hellman, for example, digital signature algorithm. So these two problems base or on the discrete logarithm problem over finite fields. In here, I will describe the simplest case when the finite field is the prime field, but also my paper archive, we can do similarly on the binary fields, or I will show later what we can else do. Okay, so we define the discrete logarithm problem in such a way, and then we can find that if we suppose that m is the bit length of ord g, so ord g is the order of element g, we then will write the exponent y on the m bits. So what is the order of elements? Maybe I will. Do you know? I don't know if I should talk about that or no.
Yes, do tell us, because I don't know.
Okay, so let's suppose that we have the following problem. 4 to the y equals to h modulo 11. So let's try what y can be. Oh, sorry, I should write h. I think that we can use 9 in here. So 4 to the power of 0 is of course 1, yes, so it's not the solution. 4 to the power of 1 is 4. 4 to the power of 2 modulo 11 is 5, yes, because it's 16. 16 modulo 11 is 5. 4 to the power of 3, it is, you can see, 4 times 5, it is 20, modulo 11, it is 9, yes? So the solution in here, I think, is y equal to 3. But let's go further. 4 to the power of 4, it is 9 times 4, it's 36. Modulo 11, it is 3. And finally, let's look. 4 to the power of 5, it is 3 times 4, it is 12, and modulo 11, it is 1. So the 5 is order of element 4, because 4 to the power of 5 gives neutral element, yes, neutral element of the multiplication. So 4 to the power of 5 is 1 in this field F11. Yes, is it clear? So it means that we know that y cannot be larger than 5. So if you know we can suppose that we know the order, yes? In the discrete logarithm problem, the order of element is known. So if we know the order of the element, we know how many bits are necessary to write this number, and we know that if the order of element is 5, to write 5, we need at most 3 bits, yes? So m in this example will be equal to 3. Okay, Paul, is it okay now?
Yes, excellent. Thank you, Michał.
Okay. So we go further, yes? So in here will be a little tricky moment. So yes, we have to write y using binary variables, yes, because we have to transform this problem to the QUBO. But even if we use binary variables in the exponent, there is a still problem, yes? Okay, we can write y as the following sum. It is, as I hope you see, the binary expansion of the number. We can use the multiplicative form to write it, but still there is a problem because binary variables are in exponent, yes? It's hard to construct QUBO problem if you have binary variables in the exponent. So we have to make a following trick. So let's look that for any of this number, we can write something like in here. So g to the power of 2 to I minus 1 times ui is equal to 1 if ui is equal to 0. I think that it's clear, yes, because then we'll have g to something like that. So it is g to 0 and it is 1, as in here. Of course, if ui is equal to 1, it's clear that then we will have g to the power of 2 to I minus 1. But how we can write it without writing binary variables in the exponent? We can do something like it's presented in here. So every number of every such number we can write as xi, and let's look that we can write it as 1 plus ui, and here in brackets we have g to the power of 2 to I minus 1 minus 1. Why this works? Because let's look, if ui is equal to 0, then in here we have 0, and the whole result is equal to 1. Yes, otherwise, if ui is equal to 1, then this one and this will vanish, and the result will be g to the power of 2 to I minus 1. So it is the crucial moment, yes? The transformation to get the binary variables from exponent to make the polynomial, yes, polynomial with binary variables. So okay, so what can we do further? So we can now write this DLP problem as the problem finding a solution to the following problem. Yes, so let's look that x1, x2, and xm is equivalent to this. Yes. So we can do this using brutal approach. So brutally, we will substitute instead of x1, x2, and xm these terms. Yes. And what will be next? We will multiply everything. But let's look that we have in here, in every bracket, we have two monomials, so two monomials, and this is polynomial of degree 1. But if we have two monomials, so we finally have to multiply 2 times 2 times 2, and so on. We'll obtain 2 to m terms, yes? From this, only one will be of degree 0. And finally, we can find that this QUBO problem will consist of 2 to the power of m minus 1 variables. So this reduction is not polynomial, but exponential, yes? So it's very inefficient. We can do this more efficient, applying the following structure. So we use the binary tree of maximal height. I don't want to now show you how I estimated the number of all variables, but using something like that, we can write the system of the following equations. So it's very similar to the example I showed earlier. So it will be some equations over finite field FP. And now if we'll try to estimate the number of binary variables in this problem, we'll find that the transformation of the DLP problem to the QUBO problem will consist of around 2n square Boolean variables. What is n? N is a bit length of the prime p, bit length of p. So we can use this polynomial transformation of the discrete logarithm problem to the QUBO problem. So I'm sorry, I will now talk a little faster because it should be about 30 minutes for our presentation. So I made some practical experiments. That time I solved using the brutal approach I showed here, the instance 4 to the power of y congruent to 27 modulo 59. So it is 6-bit prime field, and using this I talked about this efficient approach. So this is efficient approach. That time 2 years ago, I solved the following instance, as I showed an example. 4 to the power of y is congruent to 9 modulo 11. So the first problem required 18 logical qubits and 36 physical qubits. The second, 30 logical qubits and 79 physical qubits. So in here are showed embeddings of these problems in the D-Wave advantage. So from that time, I made a few improvements. So the best nowadays known reduction of the DLP to the QUBO problems is a little better because it requires 1.89 n square logical variables, but it's very technical approach. So I will only tell that in this approach, I write the exponent y using not binary representation, but ternary, yes. But I have to use to this ternary representation binary variables, so it's a more sophisticated to tell how it exactly works. But this method may be easily adapted to other problems, as the last month paper on archive DLP over binary fields. You can use such a reduction using 3n square logical variables. You can use this method to elliptic curve discrete logarithm problem. Such reduction requires, as you see, n cube divided by log 2 from n. In the case of Edwards curves, and so that we can use it for many similar problems. So in summary, I have to say that quantum annealing allows us to solve problems that are too hard today for general purpose quantum computers. Because I don't know if you heard, but I didn't hear that someone would solve using Shor algorithm such large instance as 6-bit DLT. Yes, so we can do more complicated problems nowadays on quantum annealers than on general purpose quantum computers. However, DLP, both DLP and DLP, I think that quantum annealing will not overgain Shor's algorithm, because even if we can find polynomial reduction, I think that solving this problem using quantum annealing will be exponential time. However, as I said, quantum annealing cryptanalysis has great potential, and our last paper shows that quantum annealing may be more efficient in solving algebraic attacks on stream ciphers. It may be more efficient than brute force or even than Grover's algorithm. It's of course hard to estimate because, as you know, the time complexity of solving given problem using quantum annealing isn't easy task. Yeah? So we have to make 40 rolls on this. But if you are interested in this topic, in here is the paper. It's published in ETC, Transactions on Emerging Topics in Computing. And I think that it's exactly a little more than 30 minutes. But thank you for your attention. If you have any questions, I will be happy to ask.
Great, thank you very much, Michał. Thank you for a very interesting presentation, challenging my mathematical abilities, certainly. And as Michał suggests, if there are questions from the audience, then please do ask either by raising your hand or unmuting and speaking.
Hello, Paul. Hello, Michael. Can I have a question?
Yes, please, go ahead.
It's Łukasz Dyszkowski from here. I have a question because I haven't heard in your presentation, Michael, the reasons why we should care about solving DLP with quantum computer. Why should an ordinary guy interest in breaking some problem with quantum computer, some problem which it is not used in everyday life, yeah? I don't know, maybe Paul use it, or maybe you, Michael, use it in everyday life, but I don't. So why should we care about this?
So yes, it's of course good but tricky question. Okay, so you all know that cryptography is important. Yes, if we will be able to break cryptographic algorithms, then of course our security will be much smaller. Yes, so it's okay. You all know that. Why we should take care of quantum annealing and its application to the, as I said, I don't think that quantum annealing may overgain Shor's algorithm. So from this point, it may look that it's useless. But when I was working on application of quantum annealing to DLP, I found several methods that who knows may be used to some other algorithms, or maybe someone will find better reduction of this problem, maybe to quantum annealing, maybe someone will use QAOA, and who knows, maybe someone will find some method that will be easy to adapt than Shor's, yes, and will be still a fast method of computation of solving discrete logarithm problem. Secondly, it's from my point of view important from the theoretical reasons, because if we carefully study how hard are reductions of following problems, we'll see some similarities. So in the computations using classical computers, for example, discrete logarithm problem in additive group is much easier than discrete logarithm problem in the multiplicative group and than integer factorization. And these problems are easier than elliptical discrete logarithm problem. And therefore, similarly is in here. The reduction of DLP in additive group is much easier because it requires O from N variables than DLP in multiplicative subgroup or integer factorization, which requires about O from N square variables, and ICDLP requires about O from N cube. Yes, so I think that from this point of view, it's interesting. Yes, it's okay, Łukasz?
Yes, thank you. That's perfect. So thank you for your answer, and thank you for your presentation, and thank you, Paul, for popularizing the science. Thank you for this meeting.
It's my pleasure. There was this paper came out from China maybe a week or two ago, which I've just been finding on the internet, talking about using a D-wave advantage for trying to find prime factors.
Oh yeah, so I know what are you talking about, but I don't know why it is so famous. It cannot give any advantage. Yeah? So I don't know exactly what they did. So they wrote that they factorized 23 bits, then they wrote that it was 50 bits. No matter, even if it is 50 bits, quantum annealing, from my point of view, cannot overgain Shor's. Yes. But as I thought, the things are different if we will talking about symmetric ciphers. So using quantum annealing and trying to make cryptanalysis for string ciphers, who knows, it may be more efficient than brute force or growers. Yes, so for asymmetric ciphers, no, but for symmetric, it is possible.
Okay, I'm glad to hear that internet security remains solid, at least for now. I'm very pleased to hear that.
Yes, don't worry.
Thank you for your reassurance, Michał. And any other questions for Michał before we conclude? If not, Viv, you.
Sorry, I came in rather a hurry and joined slightly late, for which my apologies. Traffic on the bicycle. So I'm just curious because I haven't looked at this since. I mean, I knew about methods proposed for factorization. So essentially, which is one of the applications of this. So there's a paper in Scientific Reports from 2018. This is Yang, it's Travis Humble's group, essentially, that did some tests on this in around 2017, 2018. Do you know that work? How does this relate?
So the method of transformation is different in my case, yes. But what is as I said here, the problem of the discrete logarithm problem and integer factorization are related. We don't know how this relation really is, but as it's known, similar algorithms works for both these problems. Yes, so we have general number field shift, which is the most efficient classical method, and this method works both for integer factorization and discrete logarithm problem. So from my point of view, the transformation of these two problems is also similar because it requires O from n square variables. Yes, so the method is different than of Junk and others, but the complexity of this transformation is similar.
Yes, because I think they're O n squared as well for.
Yes,
for
yes.
that.
For
Yeah,
the method of Junk, it was n squared divided by 4, as I think.
Mm-hmm. Yeah.
And here is 2n squared. So it's not the same, but in the asymptotica, it's asymptotically similar.
Okay, cool. So there's something underlying that is kind of the same approach to go maybe from the binary variables in the exponent.
Oh, I don't know. It's very hard to tell what is. Maybe it is very on foundations. Cryptographers don't know what this relation really is. So, but this problem are as you can see often similar. The method of solving this problem is similar.
Okay. Oh, I see. So because Shor's algorithm was really a discrete log one, but applied to factoring, those of us who don't understand the cryptographic and the complexity theory think that we know the relationship, and you're saying that we don't?
Oh, so okay, if we are talking about Shor's algorithm, of course, these both algorithms are in the same group, yes, but it's not as easy because ECDLP also belongs to the same group, yes. So the Shor's algorithm is a polynomial time both for integer factorization, DLP and ECDLP, yes. So from this point of view, they belong to the same group. But if we'll be talking about classical algorithms or even about reduction of this problem to the QUBO, it's not the same. Yeah? So reduction of ECDLP to the QUBO is O from n cube. So it's more complicated. Yes, the same if we are talking about the most efficient classical algorithm to break ECDLP. It's exponential time, yes. So there must be something more common between DLP and integer factorization.
Okay. We have lots to learn, those of us who specialize in other things and don't know this problem as well. Thank you very, very much. Great.
So thanks for question.
Good. I think we should probably conclude there. So I echo Viv's thanks for Michał. Very interesting presentation and lots to learn, as Viv points out. So let's conclude there and invite people here to re-log in next Tuesday, when the speaker will be my own UCL colleague, Rupayan Ghosh, talking about the exponential speedup of quantum annealing using n-local catalysts. So look forward to seeing as many people as possible next week. And once again, many thanks to Michał, and thank you to everyone for attending.
Thank you for the invitation.
It's a pleasure. Bye-bye, everyone. Bye-bye.
Bye-bye.